Good morning, good afternoon, good evening, and good night. Good whatever time it is where you are. Welcome to today's Math Minute, the only Math Minute guaranteed to be today and guaranteed to be no more than 10 minutes long. Although that second guarantee almost certainly is not actually going to happen. I want to do a little bit of a longer video here to address how to solve quadratics by factoring. But specifically, I want to look at a method for factoring called the box method, or sometimes it's also called the area model for multiplication. Now, because this video is going to be a little bit longer than is typical, I'm going to have, let's see, what direction am I going to be? I think I need to be pointing this direction. I'm going to go ahead and put like a, what's it called? Like an outline for this video, but you can go into the description and click. So if you want to skip ahead to different parts of the video, you should be able to click in the description to see that. Now I keep pointing over here, but now I need to actually write over there. Here's how I'm going to go ahead and walk through this process. First of all, I just want to look at what is the box method or the area model for multiplication. Specifically in the case of polynomial multiplication. So I want to look at how we use this thing called the box method in order to multiply out, for example, two binomials. Once we have figured out how to multiply out two binomials, then we want to talk about how can we do this process backwards, and that is what we call factoring. So we're going to look at factoring trinomials, specifically trinomials of the form ax squared plus bx plus c, where a, b, and c are what we call parameters. They can be anything we want, but once we've selected them, they don't change the way that the variable x would change. I want to factor trinomials using this box method, but I want to split this up into two different kinds of factoring. They're actually the same process, but they do look a little bit different. The first one I want to look at is how do we factor trinomials when a is 1? These are what we call monic trinomials, and they tend to be a little bit easier to factor. In fact, once you get good at them, you probably won't even use the box at all to factor these. And then I want to look at, okay, so how do we factor the trinomials that almost certainly do require the box? How do we factor what are called non-monic trinomials? For non-monic trinomials, a is not 1. So there's going to be some coefficient in front of that x squared, 2x squared, 5x squared, 7x squared. That's going to make our factoring process look just a little bit different. And then finally, last thing I want to talk about is how to actually use this factoring process to solve quadratics. We do that with something called the zero product property. So like I said, today's video for sure is going to be somewhat longer because we are going to be doing these 4 different items, but you will be able to click in the description right now if you want to jump ahead to one of these particular topics. So first of all, let me demonstrate what the box method actually is. Imagine that we have some initial pair of binomials. We'll start with something simple like x plus 3 times x plus 9. If we want to multiply these binomials out, there are a variety of ways to do it. You may have heard of FOIL or double distribution, this idea that we're going to multiply the first x, multiply the second x, and then eventually add up some like terms. You may also have literally stacked this the way that we do with actual numbers, like a 13 and a 19. But instead of 13 times 19, it's x plus 3 times x plus 9, and we do something that basically looks like the regular old multiplication algorithm. And again, at the end of this process, we add everything together. I'm going to suggest, however, that this particular method called the area model or the box method is the best method for organizing our work and preserving as much information as we need along the way. Most importantly, it's also going to be the best way to organize our work as we try to do this process backwards, as we try to begin with some polynomial, typically a quadratic, a trinomial of degree 2, and work our way backwards to these factors, to what we call binomial factors. But again, before we get that, let's just make sure we understand what the box is and how it's working so that we can undo it later on in this process. The box would work like this. For a binomial, we're going to draw a 2 by 2 box. 2 by 2 because each binomial has 2 terms. So we will then put our terms down as if they are the lengths of these different rectangles. This first term, x plus 3, I'll put along the top, though it doesn't matter. You could also put it down the side. And the second term, x plus 9, is the one I'll put down the side. Though again, multiplication is commutative, A 3x4 rectangle and a 4x3 rectangle have the same area. It makes no difference which dimension goes where. From here, we want to find the area of each one of these different rectangles. This is why we sometimes call it the area model. So x times x, for example, this upper left-hand corner is x squared. An x by 3 rectangle would have an area of 3x. An x by 9 rectangle would have an area of 9x. And then finally, 3 times 9 is 27. So that bottom rectangle we can literally think as a 9 by 3 rectangle with an area of 27. Just like in our typical multiplication process, again, if you imagine something like 13 times 19, at the end of that process, after we've got our partial products, that's what these numbers here are called, we find the total product by adding them together. Similarly, these boxes right now represent our partial products, and so our total product will come from adding everything up, adding the areas of all these different rectangles. You can see that we're going to have two like terms along this diagonal. That's pretty typical for how we organize these polynomials. And so our final product is going to be x squared plus 12x plus 27. So that's how the box method works. But let's imagine that we actually wanted to begin this process where we ended the initial multiplication. Let's imagine that we had some trinomial like x squared plus 7x plus 12. And we want to work our way backwards to what the factors would look like, what the binomial factors that multiplied together to make x squared plus 7x plus 12 were. What could we say about this? Well, let's go ahead and draw our 2x2 box. If it came from two binomial factors, it would have come from a 2x2 box. And you might notice there are a few things that are pretty simple to tell where they come from. That upper left-hand box is always the squared term, or what we call the quadratic term of our trinomial. This lower right-hand box, for that matter, is always the constant term. Just like in this box over here, we had our x squared and our plus 27 from that upper left-hand and lower right-hand corners. But at this point, it appears like we've lost some information. When we combined these two other boxes to come up with the 12x before, we now can't really tell when we're trying to do this process in reverse what two numbers we added together to make that 7x. There are lots of different pairs of numbers that could add together to make a 7x. It could be a 2x and a 5x, a 1x and a 6x. It can even be weird stuff like a 10x and a negative 3x. But although it appears like we've lost some information, in fact we haven't, because of this plus 12 here. Remember, in the previous example, when we were multiplying these binomials to come up with the trinomial product, it wasn't just that these two boxes added together to make 12x, it was also that the dimensions that created those boxes multiplied together to make the 27. So at this stage of the game where we're trying to do the process backwards, we haven't actually lost information, we just have to work a little bit to recover information. In this case, we need to think to ourselves, all right, I know the two boxes add together to make 7x, but I also know that these dimensions on the outside that create that sum of 7x are going to multiply together to make 12. So what I need right now is to think of two numbers that multiply together to make 12, but would add up together to make 7. I typically have my students make this little table with a space for what we call factors and a space for the sum. We know that the sum is going to be 7, and we just said that in this particular case, it's pretty clear that the product is going to be 12, although we will adjust that in a few minutes for other kinds of trinomials that aren't as simple as this one. So if I know that my product is 12, I can literally just start listing out numbers that multiply up to 12. I do want to remember that sometimes I need to change the signs, but in this case, since everything is positive, I can just stick with positive factors. And as you look at the possibilities, 1 times 12 makes 12, 2 times 6 makes 12, and 3 times 4 makes 12. Only one of those possibilities not only has the sum of 7, but also the product of 12. And so that tells me it must be a 3x and a 4x that fill in these other two boxes. For these monic trinomials, that's what we call it when it's just an x squared or n squared or whatever squared here, but there's no other number, the factoring at this stage is pretty easy. What did the x squared and the 3x have in common that could have been this dimension out here? Well, obviously x. For that matter, what times x is x squared? That answer is also x. X times what would have made this plus 3x? Plus 3. X times what would have made 4x? plus 4. Then I can always double check my work with this final box. Is it true that a 3 times a 4 would make a 12? And the answer is yes. And so we can say that x squared plus 7x plus 12 must have come from the binomial factors x plus 4 times x plus 3. So without looking at this process both going forward and backwards, let's talk just about how we would factor in general for specifically these monic trinomials. Let's consider an example like x squared plus, let's do 11x minus 26. X squared plus 11x minus 26. Here's what it would look like. If we imagine this having come from two binomials times each other, of course we know that the quadratic term, the x squared term, would have come from this upper left-hand box. That happens every single time. We also know that the constant term, the number itself at the end, or what we sometimes call c, always comes from that lower right-hand box. The only question we have to ask ourselves is what would have filled in these other two boxes such that they added up to be positive 11x. And again, it's tempting to think here that we can't do this, that we have lost information somehow. But because of the presence of that minus 26, we have actually not lost as much information as we might think. We know for sure that with these monic trinomials, that x squared term is always coming from x times x. So the only question we have to figure out is these other numbers in the binomial. We know that they multiply to make negative 26, and we know that they add up to make positive 11. So we actually do have enough information to figure out how to fill in those other two boxes. At some point, particularly with these monic trinomials, you'll get good enough to where you can probably do this in your head, and you may not even use the box at all. But never be afraid to just go ahead and write down a little table with space for our factors and space for our sum. And again, in this particular case, the sum that we're looking for is positive 11, while the factors we know need to multiply up to that negative 26. Now, in a moment, when we do some of the non-monic trinomials, we'll have to adjust this part of the process slightly. For now, we just want to list out all the numbers that multiply up to make negative 26. So it could be negative 1 and positive 26, but those of course have a sum of 25. That's definitely not matching the positive 11 sum we're looking for, so we're going to keep going. Negative 2 and 13. That has a sum of positive 11. That's the one we must be looking for. And once we find the one we're looking for, we don't need to keep listing out other factors, though certainly there may be others. In this particular case, there are no other numbers that we use, but we do change the signs. That is, we could have said it was positive 2 and negative 13, or positive 1 and negative 26. We don't end up using those because those have negative sums, and the sum in the middle that we wanted was a positive 11. But again, there are going to be other factors. All we care about is which is the pair of factors that have that sum that match our middle term. Or sometimes we say that match b. Remember, this is in general ax squared plus bx plus c. You can tell here that for this trinomial, a is 1, b is positive 11, and c is negative 26. Going back to the box, we have figured out the two factors, so it must be a minus 2x and a plus 13x that fill in the other two boxes. And again, because this one is monic, this next part of the process actually goes pretty quick. X times what makes a negative 2x? Oh, negative 2. And so that must be the dimension that goes above that second column. X times what makes positive 13x? Oh, of course, positive 13. So that must be the dimension that goes next to that bottom row. This final column and row always comes from the product, negative 2 times 13, and so it always gives us a way to check our work. Is it true that negative 2 times 13 is negative 26? Yes. And so for sure, this must have come from the binomials x plus 13 and x minus 2. If for whatever reason you weren't sure at this point, you could multiply those back out using the box method or any other method you want and confirm it genuinely is the same as this trinomial product x squared plus 11x minus 26. Now, let's go ahead and look at one that's not monic. Let's go ahead and see how we can factor using the box method for these non-monic trinomials. Remember, what we mean by a non-monic trinomial is simply that there's a number other than 1, that is a number that we actually write down, in front of the x squared term. That is, that we have a coefficient for the quadratic term other than 1. In this case, let's go ahead and try and factor 2x squared minus 11x. Let's go with minus 30. How are we going to figure out what binomial factors generated this particular trinomial? Keeping in mind, it's always possible the answer is there are no binomial factors. That is, if you try the box method, this area model for multiplication, and it doesn't work, it's not that the method is failing. Some trinomials just don't factor any further, in the same way that some numbers don't factor any further. If I told you, hey, give me the prime factorization of 17, and you said back to me, well, it's just 17, I couldn't say to you, oh, you've failed, you're not doing it correctly. I would just have to say, oh, of course, 17 is a prime number. It does not factor any further. That same thing can happen for some binomials and trinomials that we try to factor. And so what I always tell my students is that, yeah, you might not be able to factor something, but it won't be because the box method failed. It will just be because that's an irreducible quadratic. Some quadratics just don't factor at all. If it factors, though, it will factor in this box method. So let's go ahead and try it out. Let's draw our 2x2 box, of course. And again, we always know the squared term, the quadratic term, must have come from this upper left-hand corner. So let's put 2x squared in that upper left-hand corner. The constant, in this case minus 30, must have come from that lower right-hand box. And so let's put that minus 30 in the lower right-hand box. But again, we end up in this situation where we have two empty boxes that we know add up to negative 11x, but there are lots of terms that could add up to negative 11x. Maybe it's negative 5x and negative 6x. That you'll notice negative 5 times negative 6 does not make negative 30. That actually makes positive 30. So it can't be 5 and 6. Maybe it's negative 2x and negative 9x. Maybe it's positive 2x and negative 13x. But remember, it's not that just anything we can think of that adds up to negative 11x fills in those two boxes. There is some sense in which that negative 30, the product, is constraining what could go in the other two boxes. So let's go ahead and set up our table. And again, for the table, we want space for factors and space for sum. And again, the sum just always matches b, whatever the coefficient of that middle term is, the linear term or the x term. In this case, that's negative 11, as we've already said. Now here's where we adjust our process slightly. Before, what we were doing is saying, well, what multiplies up to this c, negative 26, and adds up to the positive 11? And so in this case, it's tempting to think, what multiplies up to negative 30, but adds up to negative 11. But that would ignore the fact that our other box up here was not x squared, but is 2x squared. Meaning, in all likelihood, when we factor that, that's going to come from an x and a 2x in some order. And so if this were like a 5 and this were a 6, I would end up with a problem here because these boxes would not be 5x and 6x. This box down here would actually be 2x times 5 makes 10x. And so you can see that 2, what's making this trinomial non-monic, is also affecting how those two empty boxes add together. So I have to bring that into play as I think about the numbers that I want for some certain product. Fortunately, it's relatively simple. What we're interested in are the factors not of the number minus 30, but of the number 2 times minus 30, or what we call a times c. Again, these are the parameters we looked at initially that make the trinomial what it is. In this case, a is that 2 that we already talked about should be affecting the dimensions that go on the outside of our box here. The minus 30, of course, we already know about, but we're going to multiply 2 times that minus 30, and so actually what we want are factors of negative 60 that add up to negative 11. That's what will fill in these other two boxes to help us take into account the fact that this is a non-monic trinomial. So let's go about listing them out. This time we want the sum to be negative, and because this is a negative 60, one number must be positive and one number must be negative. That's the only way we end up with negative products. Because the sum is negative 11, we want the larger of those two factors to be the number that's negative. In other words, if I chose like negative 1 and 60, for sure Or I know that's not going to add up to negative 11 because that's going to make the number positive 59 when we add them together. The larger number was positive, and so of course our overall sum is going to be positive. So I don't want to choose smaller number negative, larger number positive. In this case, I want to flip that around. I want factors like positive 1 and negative 60, because at least the sum in that case has the right sign. Now, of course, it's much too large. We wanted the sum to be negative 11, so we're going to keep going. Could it be 2 and negative 30? Well, that sum is negative 28. Closer to what we want, but still too large. Could it be 3 and negative 20? Again, we're getting way closer, negative 17, but we need to keep going. Could it be 4 and negative 15? Yes, that has a sum of negative 11, and so it is a positive 4x and a negative 15x that are going to fill in these other two boxes. This gives us the product we need. 4 times negative 15 is negative 60, but it also gives us the sum that we need. Those two boxes now correctly add up to negative 11x. And now we just do kind of a puzzle sort of thing. Look across that top row. What goes into both 2x squared and 4x? 2x itself. 2x times what makes 2x squared? 2x times x. 2x times what makes positive 4x? Positive 2. X times what makes negative 15x? Negative 15, and as always, that lower right-hand box lets us check our work. Is it true that 2 times negative 15 is negative 30? Yes. And so we can tell that this initial trinomial, 2x squared minus 11x minus 30, actually factors as 2x minus 15 times x plus 2. And so this is how you use the box method to factor these non-monic trinomials. The exact same way we did with the monic trinomials, but with the added step of making sure that we're looking for factors of a times c, not just c, when we do the factor and sum process. One more example, and I'm going to use a non-monic trinomial so we get a little more practice with that part of the process. This time I want an actual equation. When we have these trinomials, ax squared plus bx plus c equals 0, you might typically notice that we try to have a 0 on one side of this equation. This is because when we factor these, what we want is to get that factored form, blank times blank, equal to 0. The reason we want this is so that we can take advantage of something called the zero product property. If we have blank times blank equals 0, we have some important information about what could fill in those blanks. The only way you can end up with a product of 0 is if you are multiplying with 0 itself. This is either 0 times something like x plus 3, or it's going to be the first factor is x minus 8 times a 0. But one of these two factors has to be 0. All we're going to try and do is use the box method to factor the initial trinomial, and then from that factored form, we can set the individual factors equal to 0 and solve. It gives us a way to solve those linear factors for 0 directly, which will eventually give us the quadratic solutions that we want, the solutions to the initial trinomial. But in symbols, that sounds a little bit abstract. Let's go ahead and take a look at an actual example. Let's say that we have 10x squared equals 27x minus 18. The first thing to recognize here is we don't have a 0 anywhere. And again, one of the main things we're trying to accomplish with these trinomials when they're in an equation is make sure we have a 0 somewhere. Fortunately, in this case, it's not terribly hard to get a 0. We're going to add 18 to both sides to get rid of that negative 18. And in the same way, we will subtract a 27x to get rid of the positive 27x. And so what that gives us is 10x squared minus 27x plus 18 equals 0. Now at this stage, I don't want to dive too far into this process. Maybe I'll save this for another video. It's harder the larger the numbers are. And so we always want to try to see, can we make the numbers any smaller, usually by factoring out some common factor. Unfortunately, 10, 27, and 18 don't share a factor in common, not all three of them. A couple different pairs of them do, but not all three of them. And so this is it. This is the trinomial we are going to have to factor. But we're not going to worry too much much about it because we are armed with the box method. So let's take these terms and put them in the box where they go. Where does the 10x squared come from? Ah, of course, the upper left-hand box every time. Where does the plus 18 come from? Of course, the bottom right-hand box every time. And the only other thing we need to figure out is what numbers fill in those other two boxes using the factors and the sum process that we just looked at for both monic and non-monic trinomials. We want the sum to match this middle term. That is, we want the sum to be negative 27. But of course, we want the product to equal A times C. In this case, 10 times 18 is 180. So we need two numbers that multiply up to 180, positive 180, but add up to negative 27. Since they multiply up to positive 180, their signs need to be the same. So that could be something like 1 times 180. But clearly that sum is going to be way too large. So we need some numbers that are a little bit closer together. For example, 9 times 20, which is also 180, gets us pretty close almost immediately. Or I should say, negative 9 times negative 20 gets us to a sum of negative 29, which is quite close to the sum we want of negative 27. It's not quite what we need though, so I'm going to keep trying. How about negative 10 and negative 18? All right, that gets us a sum of negative 28. We're almost there. 11 doesn't go into 180, so that's not going to help us, but does 12 go into 180? Yes. It is the same thing as negative 12 times negative 15. That makes the negative 27 that we need. And so it must be a negative 12x and a negative 15x that fill out these other two boxes. From here, we do the Sudoku puzzle type thing. What do a 10x squared and a minus 12x have in common? A positive 2x. 2x times what is going to make that 10x squared? 5x. 2x times what is going to make minus 12x? Negative 6. 5x times what is going to make negative 15x? Minus 3. And as always, do these two dimensions, negative 3 by negative 6, make a positive 18 product? Yes. And so we can say that this equation we're trying to solve actually factors as 2x minus 3 times 5x minus 6. The whole thing is equal to 0. Here's where the zero product property comes into play. The only possible ways we can multiply these two quantities and have it be equal to 0 is if the two quantities themselves are equal to 0. So let's just set them equal to 0 and see what happens. Where would 2x minus 3 be equal to 0? Well, you could add 3 on both sides and say, oh, 2x needs to be equal to 3. And then divide by 2 on both sides and get one of your solutions, x equals 3 over 2. Kind of running out of room here, but let's do the same thing for the other factor, 5x minus 6. Where would 5x minus 6 be equal to 0? Well, again, you might recognize we need to add 6 to start isolating the x term. 5x equals 6, divide by 5, and we get our other solution at 6 over 5. And so this original equation, 10x squared equals 27x minus 18, has two solutions, one at the fraction 3 over 2 and one at the fraction 6 over 5. That is using factoring to get our trinomial into factored form and then using the zero product property to actually solve where those individual factors equals 0. All right, thank you for your patience. I know that was a little bit longer of a math minute. My son is over here telling me, oh my gosh, we have to go. And so we do. If you have any questions, comment down below with those questions. If this video is helpful, like and subscribe. And otherwise, I will see y'all next time.
Finally, he's done.
Finally, he's done.